Good morning, everyone, or good afternoon, I should say. It's just turned 12 o'clock here in the UK. Welcome back to this second session of Methods and Method Development. We have three speakers in the next session. So without further ado, I should introduce Sami Kaapa, who's going to be our first speaker. Sami, the floor is yours.
Thank you very much. Let me share my screen. So I guess you can see this. So good afternoon on my behalf too. I'm working at the Technical University of Denmark, and for the last 2 years I have been working with this field of global optimization. And we do that with machine learning, and we have this implementation called Beacon, which I will now present. So first of all, something about the global optimization, and let's first distinguish it from the local optimization, which is basically this. So sometimes they get mixed, so that's why I'm telling this. So for local optimization, you usually have something similar that you want to end up with, like in this case. So this is a tantalum oxide cluster. So you just basically relax the structure so that the bond lengths and angles are optimal. Whereas in global optimization, you basically don't know where you want to end up to. And so you have to start in somewhat unbiased configuration. And this is what we found in our paper for this system. So the problem we want to phrase like this. So we fix the number and types of atoms, and then we fix the potential, which is DFT usually, or it's DFT for our case. And then we want to ask which atomic structure minimizes the potential energy given these constraints. The standard solutions for this are usually Bayesian hopping and genetic algorithms. And now, because machine learning is better and faster everywhere, that's what we want to do as well. So we are using something that's called Bayesian optimization in literature. However, we are not the first ones to do this. So last year, Gaussian was published by Melthe Bispo and Björk Hammer, where they already show that this Bayesian optimization can improve the global optimization with, let's say, 2 orders of magnitude in terms of number of single point calculations. So you read this curve so that you want this to be as far left as possible, and so close to the 0 point in the x-axis. And Gaussian was basically my starting point where I started my project, but the essential difference here is that we train the model also with forces. So we have a surrogate model here, which is basically a Gaussian process, which is now trained with forces, and we use a fingerprint that takes into account the natural symmetries of the system, such as rotation and translation and permutation. And well, I would like to go through this cycle here. So we start with some DFT calculations here, and we evaluate the forces and energies for those structures, and then we can train the model with that data. After that, we create some random structures in some special way, and we can relax those structures using the surrogate model. And once we have done that, we have relaxed structures. We choose the best one of these structures by looking at the values of energy and the uncertainty. So this function is called acquisition function, and we just look at the energies and the uncertainties that are given by the Gaussian process for each data point. And we select one structure based on this. And for that structure, we evaluate another DFT calculation and update the model, which means that the model gets improved in accuracy, we hope. So, and then we can go through the cycle again and again. And finally, we get some database of structures with energies, and we look at the lowest energy one and assume that it's something that we want for a global minimum structure. Let's look at the model for a second. I'm not going to show the equations for Gaussian processes, but we can have a look at this simple system here, where we move a copper atom in one dimension. And because this is such a simple system, we can actually calculate the full potential energy surface, which is the orange curve here. And if we take a training point here, we evaluate this point here and make a Gaussian process with the fingerprint and with the forces, we get the blue line, the predicted potential energy surface, with just this single training point. So 2 points here. One is that we are training on the forces, so which means that we get this gradient here correct. If we didn't do that, we would get just a straight line here, if we get the prior correctly. The second point is that since we are using a fingerprint and the permutation symmetry, we know that there are these features here, which you wouldn't get if you would run in the coordinate space only. So as I said, we are using Gaussian process, and we want to calculate the uncertainties as well. So if we do that, we can get the uncertainties here and calculate the acquisition functions. And now the minimum point is here. We add another in beacon. We add another training point here, and this is what we get. So now the predicted line is very much what we want already. And the next point would be selected in the true global minimum or close to that. So this was pretty impressive for us. And then when we go for more complex systems, we get success curves like this compared to GoFi. So the main goal for the project was to reduce the number of DFT calculations, and that's what we found. Well, this is global optimization, and it's very general, I would say. So we have tested this on clusters and surfaces and layered structures and bulk systems. And the most recent improvement is that we can also optimize the unit cell in the surrogate potential, which was used, for example, here with the MOS2 structure. So the set coordinate of the cell is fixed, but the cell could be varied in X and Y directions, and we finally got the correct bilayer structure that we expected. All right, another idea that we came up with is kind of an extension to beacon, so the interpolation between chemical elements. So if you look at this structure here, which is a gold copper bulk system, and you change 2 atoms here, which is then the first structure on the left side, and you do a net calculation, so a notched elastic band calculation from here to here, you find that the energy barrier is something like 15 electron volts. But the difference between these structures is just the elements of these 2 atoms. And we wanted to see if we can interpolate between those elements in the surrogate space by tuning the fingerprint. I'm not going into details, but the magic happens in the fingerprint. And we see that in this x-axis here, we could just use some local relaxation algorithm to get from here to here, which was very nice. So we can optimize the ordering by interpolating in this chemical element space. And this is basically what it means in practice. So this is also a copper-gold system, and we start with random fractions, which we then optimize here along the x-axis, and we finally get to the true global minimum structure, which is this kind of layered thing. Yeah, so this is one local relaxation starting from random structures in the surrogate space, and the training set size here is 4. We have 4 DFT calculations before running this local relaxation, which is quite impressive, I would say. And then we could attach all of these local relaxations into Beacon. And what we find is that, for example, the 64 atom unit cell with this structure can be optimized. The ordering can be optimized within 4 DFT calculations, or we get pretty good estimate after 4 DFT evaluations. Another thing that you can do is optimize the coordinates along the way, in addition to the elements. And for these 3 clusters, we can show that it performs much better than Beacon only, because Beacon cannot jump in between the barriers, such as the ice idea. All right, that was basically what I had to say. Something about the future. Well, things can be improved. So we have a surrogate model where we have some parameters and kernel functions and fingerprints, whatever. This can be improved, I guess. Also, optimizing the training set in some intelligent way would be a nice thing to do. And basically, right now, the local relaxations rely only on random searches, which don't have much chemical intuition. But if you plug that in, then you basically give some kind of idea what you want to get out from the runs, which may improve things, and it's clever. Yeah, and as Ice Beacon also showed, the surrogate models can enable new ideas that you cannot think of within just DFT or more complex calculators. Okay, the acknowledgements go for people here, and the money comes from the Willum Foundation in Denmark. And thank you very much for listening.
Thank you, Sami, for that very interesting talk. So please, if you have any questions, ask them in the Q&A tab. That makes it much easier for other researchers to upvote them and to track which questions have been asked and how that's working. So you left us a few minutes for questions, which is great. One thing I wasn't clear about, I think you actually hinted at in the very last slide, was you said you got your Bayesian optimization. You haven't said how you're generating your different structures. Do I understand you're just doing random structure search with this surrogate model?
Yes, that's right. So I guess you can see my window still.
Yeah, it's a question of how do you generate the different structures to start with for your relaxation. You've got a local relaxation, but where do the different starting structures come from?
They are randomly generated in some way. I mean, you can decide it yourself.
You gave the example at the beginning of this metal cluster, and you started off with a linear chain, and it ended up with this nice compressed structure. You'd have to do quite a lot of mutations on that to go from the first to the last. Are there any kind of learning of structures, like a genetic algorithm kind of thing, to breed better structures from what you've done?
Yeah. So well, technically, when you have this structure generator class, you give it basically this information, the number and types of atoms. And then if you have some constraints, you can fit those in. For example, in this case, everything is put randomly inside the cell, the unit cell. Okay,
thank you. So we have a question in the Q&A. Thank you, Lara. I'll put that on the stage. Could you elaborate more on the optimization, specifically when you were talking, I think, about getting the DFT in there and 4 optimizations for the training?
So we are not doing DFT relaxations, if that was the assumption there. We only all the relaxations are done within the surrogate space, and I guess this is what was referred to, the 4 DFT evaluations. So we have an initial training set with this lattice, but with random elements. I mean, random ordering of the atoms in the cell. And we can calculate DFT for those structures and make a model out of that.
Okay, thank you. Hopefully that answers Lara's question. Lara, please ask back if you need any more information. And Massimo asks, could you elaborate on how you update the model with the new best configuration?
That's basically training the Gaussian process again. So you get the energy and the forces, and you know the structure. So you know the features and your targets. So you can retrain the Gaussian process. And it's that simple.
Okay, thank you very much indeed. So do we have any more questions from anyone? Okay, well, let's thank Sami. Sorry, just at the last second, Jordan pops in with a question, just as we're about to let Sami off. Let me just add in that one last question. How are you getting your initial training set? Do you start with a single structure and evolve the model via your cycle, or do you start with a larger, more substantial training set?
Typically, we start with 2 random structures. We generate the structures in the same way as we do for the local relaxation, or the initial structures for the local relaxations. And yeah, that's what we do. So initially, we have 2 DFT structures. And after 1 cycle, we add 1 training point.
Okay, so it certainly sounds a very efficient approach. I'll have to look into it in more detail. Thank you. So let's thank Sami, and I'd like to invite David as our second speaker. If Sami is thank you, Sami. David, if you'd like to share your screen and unmute yourself, I'll give you a warning when you've got a few minutes left to go on your session, okay? So, David, the floor is yours.
Hello, can you hear me?
You're quite quiet. Can you make yourself a little louder?
I'm quite quiet. I can speak louder. Better?
Yep, that's better, thank you.
That's better. And can you see the slides?
Yep, going through fine.
Okay, yes, hello everyone. It's a pleasure to be here, and I'd like to really thank the organizers for giving me the opportunity to talk in this conference about all the exciting research that we have been doing over the past 1 year during my PhD. So I'm a PhD student, just starting my 2nd year in the group of Gabor Csányi in Cambridge. And so I'll talk to you about the work that we have been up to over the past year. And I think let's get started. So the outline of my talk is basically as follows. So I'll quickly motivate the work that we are doing on atomic cluster expansion force fields for molecular systems. And then I will talk to you about atomic cluster expansion, which I will abbreviate as ACE. So ACE, as I look at it, is really the most general recipe for creating descriptors of atomic neighborhoods or environments. And so I will tell you why I think this is the most general of them, and this is also the most efficient, I'll argue. And then I will demonstrate that these neighborhood descriptors are actually remarkably good, so good that you can get away with linear regression. So you can do just linear regression fitting on them, no GPs, no neural networks, and still you can get competitive accuracy, sometimes even better than all the other methods. You can get speed, it will be extremely fast, and you can also get extrapolation, which the other methods may not be that good at. And then I'll just quickly sort of summarize what future work we are planning to do and what challenges we are still facing. So just as a motivation, organic force fields have basically two kinds nowadays. There is molecular mechanics, and there is the machine learning word. And so the molecular mechanics really builds on these physics-inspired functional forms, which is one short-range part, usually made up of kind of bonded terms, parameterized using like harmonic springs, and then there are the angle terms, and there are sort of dihedral torsional rotation terms. And they're all kind of having one or a few parameters each. Whereas the machine learning force fields, that here I am listing a few, so the neural network ANI, or similar to the Baylor parallel neural networks, or a GAP, which is a GP, and then there is a NACWIP, which is a graph neural network, kind of a generalization of Schnedt. So these have a very flexible, very general functional form without any kind of restrictions. So what's interesting in molecular mechanics force fields is that their short-range part is body ordered. So they have a two-body bonded terms, angle terms, which is a three-body term, and then they have these dihedral torsional four-body terms. Whereas these machine learning force fields usually look at an atomic site energy, so they predict the contribution of each atom as a function of its neighborhood, but then there is no kind of explicit body ordering in the functional form. And we will see that this is actually important to have. So then there are some things, some other kind of technicalities that the molecular mechanics force fields have a fixed topology. So the bonds are not allowed to break or form, except for some generalizations like XFF, but they are a bit different. Whereas these machine learning force fields are topology free. So you can all of the carbon atoms are, for example, identically treated, and bonds are allowed to break and form, at least in principle. So the other kind of major difference is that these traditional molecular mechanics force fields have relatively few parameters, whereas the machine learning force fields typically have a very large number of them. And then the fitting kind of strategy is also different. The molecular mechanics force fields are often parameterized to reproduce both quantum mechanical but also experimental observables and values, be it density, viscosity, or other experimental observables of interest, whereas the machine learning force fields are typically ab initio in a sense that they are fitted to quantum mechanical data. So atomic cluster expansion, in some sense, will be in between the two. So I will first quickly introduce what ACE, or atomic cluster expansion, is, kind of mathematically giving you this recipe of creating these ACE models, and then you will see why I think that ACE is, in some sense, a generalization of molecular mechanics, which is kind of a best of both worlds of machine learning and also of traditional simulation approaches. So the way ACE starts is to write the energy as a body order expansion. So basically we say that, okay, we want to get the energy of atom I as a zeroth or a one-body term, which is kind of like an isolated atom energy, just the atom in vacuum. And then we look at the pairs, so look at each one neighbor, and then we look at these two-body contributions, similarly to the bonds. And And then we look at three-body contributions, but these are going to be quite general polynomials. So these are not going to be as simple as the ones in the molecular mechanics. But the philosophy is very similar. We have this body ordering. And then, so for a construction, it's essential to define a basis set, which is going to be, I will call it a one-bond basis functions. And this is a product of a radial function, which can be Chebyshev polynomials or anything else you like any set of orthogonal polynomials. And then these YLMs are the spherical harmonics that should be familiar from sort of angular momentum quantum mechanics. And they are going to be very convenient to obtain rotationally invariant basis functions, because the energy has to be invariant with respect to translating a molecule, rotating a molecule, inverting a molecule, and also with respect to permuting like atoms. Right. So then what we have to do is we have to consider the atomic neighborhood density. So this is a construction that was, I think, first introduced in the SOAP gap paper. And what we look at is we are basically imagining that we are sitting on a central atom and we are looking at our neighborhood within a cutoff distance. And then what we do is that everywhere where there is an atom in our neighborhood, in this spherical neighborhood, we put a delta function. So basically, this atomic neighborhood density is going to be a sum of delta functions within a cutoff. Okay, so that's what I call the neighbor density or neighborhood density. And what we do is that we'll expand this neighborhood density in this basis that we have just defined. So this is in some sense a discretization of this density into a basis. So that's mathematically that looks like this. So basically what we will end up with is, because these were just delta functions, we will end up with these one-bond basis functions evaluated at the neighbors. So this Rij is a vector pointing to the neighbor. So that's great. That's the start. And then what we do is then we will take products of these functions that you obtain this way, and then we can get basically a body ordered expansion for the energy. So we say that the energy is going to be the sum of these two-body terms in some sense. So and then this is going to be three-body, and this is going to be four-body term, and so on. Here I have omitted the one-body term because that is just a constant. Right, so let's try to make it more clear using graphical representation. So this is here I'm at the central atom and I have three neighbors, and then I evaluate these one-bond basis functions on each of the neighbors. So that's how I discretize this atomic neighborhood density, and then I take products of this neighborhood density with itself. And you can see that this is, if I don't take products, then this is just a two-body function. This is going to be a sum of two-body functions. If I take a product with itself, then what I get is a sum of two and three-body functions. So this is going to be basically a general three-body function. And you can see that if I took a product of three of these, 1, 2, and 3, then what I would get would be a four-body function. So you can see that basically I can get high body order functions without having to sum over my neighbors. And this is going to make it extremely efficient because I'm just taking these products of these projected densities. Okay, so this is something that we have nicely written down in a few papers. One of them is our most recent one. You can kind of familiarize yourself with this idea, but the key is that this way we can get basically four-body, five-body functions at constant cost. Compared to the two-body, so that's pretty brilliant, and that's something that if you wanted to actually sum over all triplets or quadruplets, then that would be combinatorially expensive, and you would never be able to do that. But with ACE, because we go via this density trick and projecting the density and then taking the products, we actually have access cheaply to high body order functions. So I think that's great, but what I have not talked about yet is rotational invariance, because what we see so far is going to be translational invariant, because we look at the neighborhood of an atom, so that's going to be just interatomic vectors. That's good. We have translation invariance. We have permutation invariance because the function depends on the atom type, but because we are summing over the neighbors, the sum is a permutation invariant operation, so that's fine. But we also need the rotational invariance, and to do that, we basically we have to formally integrate over all rotations. And what that means is that we actually have to take these spherical harmonics and multiply them using the corresponding Clebsch-Gordon coefficients. So that's kind of like a big lookup table that has been worked out conveniently a long time ago. So basically we get these B basis functions by kind of taking the Clebsch-Gordon coefficients and multiplying them with the corresponding YLMs, so that we get a rotationally invariant combination of them. And we have some other selection rules, for example, to make sure that it's also invariant with respect to inversion. And then we get this final expression for the energy of atom I in terms of these B basis functions that we obtained after rotationally averaging these A basis functions. And then what's great is that we can attempt to do linear regression using this. So these C are the coefficients that we are trying to fit. And all we will do is just take these rotationally permutationally invariant polynomials, which are body ordered, and just do a simple linear regression on them. By simple, I mean it has to be regularized linear regression, because as many of you will know, that polynomials are oscillatory like crazy. So one would think that it's even hopeless to fit nice, smooth force fields using polynomials. But what we can do is we can actually do a least squares regression using regularization. And the nice thing about this, so this looks like a simple ridge regularization, but with this gamma here, we can actually impose a smoothness prior. We can make sure that we penalize large coefficients on highly oscillating basis functions more compared to the smooth basis functions. So this way we allow large coefficients on smooth basis functions, but we don't allow large coefficients on the very oscillating ones. So using this kind of clever regularization, we can actually get a gradient-free regression with like dense linear algebra solvers, and I get out actually nice smooth potentials. So what we get is actually going to be accurate. So MD17 is one of these standard benchmark data sets for organic molecules, and the task is to fit a force field on a 1,000 geometries sampled from an ab initio molecular dynamics trajectory, and then evaluate it on an unseen test set. And what you can see is that ACE, so our linear regression model, actually outperforms all the other models, which include Gaussian process regression as GML, FCH, and GAP. It includes the neural networks like ANI. It is an empirical force field that we also tried, and this is like graph neural networks, different flavors of them. So you can see that basically across all of these models, these ACE features are so powerful that just linear regression on them lets you be competitive or some very even better than the best kind of AI machine learning regression methods out there. And that's not all, because because we do this linear regression and with this clever density trick, what we get is that actually, if we put the time of a force call with respect to the error, what we get is that ACE is not only the most accurate model, but it's also the fastest for any given accuracy. So say you want a model that's 10 milliV per angstrom accurate, then ACE is going to be the fastest that you can get. And what I control here is the different kind of polynomial degree and body order of the ACE basis. So the higher polynomial degree you allow and the higher body order you allow, the more accurate your model gets, but it also the longer it takes to evaluate. But you can see that ACE is in some sense optimal across all of these different models. And it can also do extrapolation far from the training set. So what I'm plotting here is a dihedral torsion of this azobenzene, and how the energy changes as we rotate along this double bond here. And what's interesting is that the training data has not much, only in this range of 180 to 160 degrees. And we see how smoothly and nicely the different models can extrapolate. And you can see that ACE, there are different flavors of ACE here, but basically what you can see is that these flavors of ACE actually capture very, very nicely and smoothly the increase in energy as this double bond is rotated. And this is not the case, for example, for GAP, and some other models also kind of do it as well. And another example along these lines is what happens if we remove a hydrogen atom from ethanol. So we just break this OH bond. And you can see that we basically, we scan along this coordinate, and you see that DFT kind of predicts this shape that we would expect. And then the ACE is the only model that is able to reproduce the shape of this curve qualitatively. Obviously, it's not getting the energy right in the limit because it has never seen a radical, but still we can see that ACE is nicely and smoothly extrapolating, kind of capturing the correct physics. That is not, that it has no chance of seeing. Like, this is the sampling of this OH distance in the training set. You can see it's only down here. And all of the models do very well here where the training is, but ACE is the one that most physically and most smoothly can extrapolate into like asymptotic limits. And to go to a more realistic system, this is my last example that I want to showcase here. We came up with this new benchmark where we took a more kind of realistic drug-like molecule, which is this 3-BPA. So this has 3 bonds here, which have all 3 rotations around them. And then we created 3 different training sets and test sets. One sampled at 300 Kelvin MD, one at 600, and one at 1200 Kelvin MD. And you can see that as the temperature is increased, the sampling becomes more and more complete in the space of these 3 dihedral angles, alpha, beta, and gamma. So here, there are very much stable pockets. And then at 1200 Kelvin, we are basically sampling the whole configuration space. And then we fit a model at 300 Kelvin data only, and then we test it at different temperatures. And you can see that ACE is actually very nicely extrapolating. Looks like only this ANI model, which was pre-trained, so that's a bit of a cheating, but anyway, is the one that can extrapolate better to high temperatures. And then when we fit on a mixed temperature training set, then ACE becomes better by quite a large margin than any of the other models that we considered here. And then as a last test, we also looked at this dihedral torsional scan. So what happens if we fix the beta angle and then we scan through different versions of alpha and gamma? So basically we do these rotations. And then what we find is that compared to DFT, the ACE and the SGDML are the ones that are kind of very faithfully reproducing the features of this torsional landscape, energy landscape. But SGDML is getting the position of the global minima wrong. ACE is getting it roughly right. Whereas the other models, the neural network, the GP, and the empirical molecular mechanics force field are really, really struggling with this exercise. And you can see that this is actually a very, very difficult task because these white dots correspond to the training data that's kind of near this plane in the dihedral torsion space. And you can see that there isn't many training data points, and there are some regions where there is none. And you can see that the nice and smooth atomic cluster expansion force field is actually able to describe parts of the configuration space where there is little or no training data. So to summarize, I was trying to demonstrate that the atomic cluster expansion potentials and linear force fields are fast and accurate for molecular systems. They are pretty simple to parameterize using least squares regression and gradient-free solvers, and they show good extrapolation properties and smoothness. So with that, I'd like to thank you for your attention. The codes that were used for this work are written in Julia. So there are these 2 Julia packages, ACE.jr and ipfitting.jr. So ACE is the actual sort of potentials, and the ipfitting is for the fitting. And I'd like to thank Kas and Christoph, Christoph is the main developer of ACE, and Kas with ipfitting is a student of Gabor. Gabor, obviously, for the help, and Yuri, Alice, and Danny were also helping in different parts of the project. I'd like to thank AstraZeneca for funding, and I'd like to point you to this beautiful preprint that we have on ChemArchive with all the results and a lot more. Thank you.
Thank you, David. Very well timed talk. So excellent. Got time for a couple of questions. We have a question in the Q&A. Is there any chance of getting an error estimate with ACE and any way to improve the accuracy? So what are your thoughts on that?
Yes, so that's something that somebody in our group is working on. And so what you can do is, because we are doing gradient-free optimization, it's a convex optimization problem, least squares regression. You can't get a committee out from the way I have shown here, the way we have parameterized these ACE potentials now. But what you can do is Bayesian linear regression, where you are learning a distribution over your coefficients. And then you can draw from that and get a committee. And it turns out that you get actually pretty good uncertainty estimates from these Bayesian linear regression fitted ACE models. So the answer is yes, but I haven't, not quite the way I have done it here.
Thank you. I also have a quick question. So you've shown that ACE works very nicely for molecular systems. With a simple change of basis function to make it work, could it make it work for crystals, for solid systems?
So that's something that has been done before. So that was before I started my PhD. So they have, I think, like two or three papers already on silicon, copper, and some other materials. I think it's mainly silicon and copper, but they have shown that ACE is actually outperforming both in terms of speed. For something like the silicon potential that they fitted using ACE was, I think, like 40 times faster than the silicon gap potential. So it's really a step forward in terms of the time and length scales that one can reach using ACE. And it was also as accurate as the silicon gap, and it was getting right certain smooth extrapolation limits that the silicon gap wasn't. So I think it's really promising. And for material systems especially. So I was really concentrating on molecules, and that's my PhD and with AstraZeneca, so I have to do molecules. But others in the group are yes, working on material systems, and it's really good.
I thought so. And finally, a question from Jarvis. Are the resulting ACE models differentiable? Do you use forces in their fitting or just energies?
Yes, so we do forces, and you can do virials. So differentiable. So the nice thing is that what you get from ACE is that these basis functions are just polynomials. So you can write them down on paper. So they are going to be R times cos theta times these. I mean, one of the ACE papers actually has in the appendix a lot of them written down, and they really look like nice analytical polynomials of like angles and distances. So you can even differentiate them on paper. But the reason why they are so fast is that because we actually implement the adjoints by hand, and so they are fully differentiable and very efficiently as well.
Okay, well, let's thank David again. And thank you very much. And I'd like to welcome to the stage Kazuki. So Kazuki is the final speaker of this session. So Kazuki, you have about 17 minutes for your talk. I shall give you a warning. And then if you go much over that, then obviously the time for questions will be reduced. But we'll try and squeeze some questions in for you. So Kazuki, the stage is yours.
Can you see my screen?
Yes, that's going through fine. You're a little quiet, but you're coming through.
Okay, so I would like to start my presentation, Encoding Distortions in Perovskites for Machine Learning Applications. So I will skip the implementations and the theories for this presentation. So if you're interested, please see this my GitHub page or the Chem archive paper. So before starting, I would like to acknowledge the collaborator Dan and supervisor Aaron and Keith, and the material design group at Imperial College London, and also my funding bodies. So I think many of you are already satisfied that machine learning has been successful in image processing or natural language processing. So this success, the underlying mechanism under this success is actually the clever way of designing the machine learning architectures. So if you see this convolutional neural network for image recognition, this architecture is suited to treat local details and the overall pictures. And if you look at this LSTM, which is capable of learning correlation in long distances. So if, for example, if it was a sentence, first word of the sentence might be important for understanding the last part of the sentence. So such architectures are designed to treat the domains very efficiently. So how is the situation in material science? There have been many successes to building a specific model that are designed for materials, but at the same time, people have been trying to import computer science models from to use it for machine learning applications. So this is only one example, but some people have encoded crystal structure into this type of box cells and effectively used image recognition algorithm to train an unsupervised learning model. So as long as I have read their paper, it seems to be successful, but typically these type of approaches require many data because the knowledge of domain isn't built into the model. And if we want to use a small data set, which is often the case in material science, we want to use efficient material representation. So before going to details, let's see what's the problem we are dealing with. So in, let's say there was an atom with lone pair. So lone pair might displace some atoms in the neighboring, creating a symmetrical environment. If it was a perovskite-like material, slight distortions of atoms may induce periodicity, global periodicity. Or if it was a Yann-Taylor type material, it might correlate with Yann-Taylor in the neighbor and make orbital ordering. So these are all local properties, but globally, such a local property affects the global property. So local structures are quite important. So in this study, we focus on local structures rather than the global structures. So this is an example, but how could we encode local structures? So the most straightforward way may be to just use a vector of atomic coordinates. Of course, all the information is in here, but it's quite redundant. And as I said, this might require a lot of data to train. On the other hand, let's say if we use average location or maybe average bond, such a averaging often smears out the important structure. But on the other hand, since the vector is small, it requires less data. And
Kazuki, I don't know if you're aware, but a lot of people are saying in the chat that your screen share seems a bit distorted. On my screen, we've got your slides in the middle, and then there's a remainder of the original title page around the outside of it. Could you try doing the screen share again?
okay.
We are getting the content, but it's quite distracting to see the frame of the slides.
I'll try to share the PowerPoint directly then.
That's probably best, yeah.
Is this better?
Yes, that's much better. Thank you. Yeah,
Okay.
that's working fine.
Okay, so we would like to encode a local structure. So our approach is to use a group theory and irreducible representation. So let's say we have an ideal octahedra like this, and the octahedra within the crystal is distorted from this structure. So rather than encoding the structure itself, in this study, we encode the distortions. So what we do is to prepare some kind of basis set using that is compatible with irreducible representation and project the distortions onto these basis set and obtain the amplitude. Of course, this is based on group. It's based on group theory, so it doesn't have to be octahedra, but I will focus on octahedra for example. So perfect octahedra follow OH symmetry. So this is a so-called character table. So these rows are all irreducible representations, and this column is group operation that leaves this octahedra invariant. And this space is actually 6-dimensional atomic basis and product space of 3-dimensional basis set, making it 18 degrees of freedom. Within this, it has 3 rotation and 3 translation. So our goal is to calculate 18 basis set compatible with irreducible representation. So the tool we use, this is already done many times. So this is not necessarily our original, but what people do is to use so-called basis set generating machine. So this basis set generating machine has a feature that extracts irreducible representation compatible part out of a function. So it's basically like breaking a function down into a basis set. So the ingredients for this is a character of the irreducible representation, which are available from the character table and the projection operator. And how we practically implemented it is that we define a vector residing on atom. So this is a bit arbitrary, but we define an arbitrary vector and apply group operation one by one and see where this vector moves. And we add up this vector, and the sum is compatible with the irreducible representation. So these are the 18 different bases that we obtained. So you might notice that first 3 are free rotation, and second 3 are free translational, and all other modes. You might have seen some of these. Although this is quite systematic, because we have chosen arbitrary vector, there's arbitrariness in this method. So for example, in T2U distortions, it looks like this. So depending on how we choose the initial vector, any linear combination of these might arise in the final vector set, basis set. And we want to remove this arbitrariness, because if the octahedra may be in different configuration within the crystal, even if it's symmetry equivalent site, and we want this framework such that the encoding for those symmetry equivalent octahedra are identical. So we decided to average this degree of freedom. So this is slightly technical maybe, but let's say there was a 2-dimensional irreducible representation. So if there was a distortions like this, within this specific choice of the basis set, the amplitude will be, of course, the norm with respect to these basis sets. So this is psi I and psi 2. And actually, the choice of the initial vectors only moves this point around in the circle. So of course, in this case, you might intuitively understand that the invariant here is the distance from the center of the circle to the surface of the circle. So it's just taking a Euclidean distance from the center. Similarly, if it was 3-dimensional irreducible representation, it would correspond to a distance from the center of the sphere to the surface of the sphere. So by doing this, we were able to obtain a single value for a single irreducible representation, regardless of the dimensionality of the irreducible representation. So just to sum up what we made, so let's say there was distortions like this, we would prepare a different basis set. So if this was EG basis set, we would have 2 if it was T to G, we have 3, we would have 3. And we will use this averaging to obtain a single scalar value. And in case of octahedra, removing rotation and translations, we would get 4 dimensional vector size of 4. So this is what we have developed, and we actually applied this to our materials project, materials of the origin obtained from materials project. So we obtained 46,000 materials and screened material with AbO3 composition. So we had a perovskite in mind, but of course we have different polymorphs of AbO3 inside here. And this resulted 552 distinct sites out of about 500 materials. And we have applied the projection and also analyzed connectivity to see what kind of materials are in there. So this is a plot of the T2G distortion against T1U. You could clearly see clustering here that is well separated from the remaining data points. And this coloring is according to the connectivity of octahedra. So the red is the case where there's 3-point sharing and 1 phase sharing. Green's case of 2 phase sharing, 3 is edge sharing, and 6 is 3-point sharing. And if you look at the actual material and the site, it corresponded to this type of site within the hexagonal phase material. So actually, there are many choices because this phase connecting network could elongate a lot in C direction, but consistently, all these red dots were the edge site of the one-dimensional octahedral phase sharing network. And this implies that strong distortions on this edge site that cannot be observed in different type of connectivity. Furthermore, if you plot it against the additional different axis, T2U axis, we see that this edge site separates into 2 clusters. So one that has T2U distortions and one that doesn't have T2U distortions. And if you look at these materials, majority of them belong to strontium chromate, and they're different polymorphs. So actually, I should have emphasized that if there was material like this very large one, we would have multiple points here because we would have many incongruent points. So there's something unique about this material. So we performed density functional theory on these materials using hybrid functionals. And these are the result. It might be a bit small, but one thing that might be interesting to see is that this cubic-like phase is the only one that has been reported up to date. In reality, I think in experimentally, this is not cubic, but rather temperature average cubic. So if you see the snapshot of this material, it's probably distorted, but the connectivity of octahedra is fully point shared. And these hexagonals one aren't reported up to date. And if you see the band gap, so the bottom 3 were metallic, whereas these top 3 were insulating. And these ABC had polar space groups, so possibly having a pyroelectric behavior, whereas these 3 were non-polar, so it cannot have spontaneous polarization. Also, these top 3 are anti-ferromagnetic, whereas these 3 were reported to be ferromagnetic. Of course, these such multiferrotic materials are very difficult to treat, so maybe you need higher level of theory like DMFT, but within this hybrid functional DFT, we could expect that there's very interesting behavior depending on the subtle change in the stacking. I should have mentioned that the difference between C and D is that C and F is that whether it has a T2U distortions. So probably experimentally, I think this one's higher temperature phase of this one. So it's probably T2U averaged due to temperature by temperature smearing. So these are 4 conclusions. So distortions could efficiently be encoded using group theory, and doing such an averaging are favorable for machine learning applications, and octahedral connectivity and local distortions were closely related, and strontium chromate may be interesting material to study. So thank you for listening.
Thank you indeed, and excellent timing. So, do we have any questions from the floor? So it seems to be a very nice approach for characterizing these different classes of materials, and yes, the clusters appear spontaneously. Do you actually find that there's any chemical similarity or functional similarity if you look at those materials in a cluster? Is it a useful way of kind of grouping different perovskites together that wouldn't necessarily be obviously clustered together in this way?
So yes, I've done this analysis, but it was quite difficult because so first of all, this all data set is restricted to oxygen, AbO3. And if you look at transition metals, it seems that there wasn't a consistent trend within there. That's because we are not actually including the most stable structure, but we are also including high temperature phase and other non-ground state structure. So maybe if we do restrict our analysis to ground state structure, we were able to get a trend, but we haven't done that.
Okay, and with that strontium material that you were looking at the end, there were 6 phases, but only one obviously would be the ground state. Are the others high temperature or high pressure phases? Have you looked at the density and how they might change from one into the other?
So this study is computational, so I don't really know how to synthesize it. But as far as the density functional theory predicts, these top 3 are have lower energy compared to this cubic one. So from the viewpoint of computational, I think it should be realizable. However, maybe it is that the synthesis or is difficult, or maybe there's certain type of defect that makes it difficult to realize.
Yeah, but if you do something like a phonon calculation on these phases, do you see that they are mechanically stable? Is there a pressure-driven phase transition or something like that which you could detect?
Yeah, I think that's possible, and possibly, for example, these are we predicted to be thermodynamically related, so calculating phonons might actually show some clear trends between distortions and temperatures. I think that's a good idea.